In the next section, I want to briefly recap dynamic programming as an algorithm design paradigm. This will certainly have been part of some undergrad algorithms modules, so I'll go quick. But I think it's worth, first of all, I like the template that I'm going to show you. I think it's worth to reiterate that. And it also means for the other algorithms, we can stop at a certain level and leave out the automatic part. I think overall that makes the presentation still more concise and more enjoyable, maybe. The way I teach this, I say dynamic programming has these 6 steps. And I'll show you on the example of edit distance what I mean by these. We always have to define what subproblems are of the original problem. And we have to somehow solve the original problem as a special case of one of these subproblems. Then to make progress, we do a local brute force step, which usually means guessing one part of a solution, but then trying all possible guesses. And from these 2 things, we can formulate a recurrence for the cost of the solution, or the quality of the solution in general. The other 3 steps, then once you've done this and you understood the general recipe, are automatic. You can turn the recurrence into a simple implementation that just memorizes the values. You can also replace this by, in practice, certainly more efficient bottom-up table filling algorithm. And so far, these 2 algorithms just give you the quality of the best solution. If you want to compute the actual solution, that also is always a mechanic process called backtracing. That's essentially a meta algorithm. It's an algorithm that generates an algorithm. And that one finds you the best solution. Okay, so the first 3 steps are where the creativity and insight into the problem are needed. The rest is automatic. If you want to prove correctness, you do this at the level of the recursion. And you can also guess what the final time is. Here, like, that statement is true if you stick to the recipe precisely. We'll see some cases where you can modify then the algorithms by using additional knowledge about the problem and kind of beat the trivial solution, the trivial algorithm that comes out of the recipe. But in general, the time you get from just following the cookie cutter approach, you get the number of subproblems times the time you need to find, to go through all the guesses in one of these subproblems. And that product gives you the overall time and oftentimes also the space. Let's see this in action. So for edit distance, assuming you've seen this before, maybe it doesn't come as a big surprise. If you have a prefix of the 2 sequences already aligned, so you've constructed a prefix of the alignment or edit script, then the question is, what will this next column look like? And really, there's only 3 options. It can either be one that looks at the next character in each of the 2 strings, or it could be an insertion, or it could be a deletion. And you have to pick the best out of these 3 options. And because the overall cost of an alignment is additive, we count the number of edit operations. Each of these contributes a certain amount. These always contribute 1. This contributes 1 if the 2 characters differ. In each case, you know what to do. So if you map this onto the 6 steps, what you do for the subproblems is take prefixes of the 2 strings. So any positions in the range of the strings give you a certain prefix, and these are all our subproblems. The guess, as I said, is what the last column of the alignment looks like. And I guess at this point, we can also say the original problem is for I equals n, m, and n equals j, j equals n. That solves our original problem because then I've taken the whole strings. And that gives us a recurrence for computing the edit distance that directly follows this subproblem structure. if one of the two indices is 0, so I'm taking nothing from one of the two strings, but there's some parts from the other string. Well, let's take the first one. If I take nothing from the second string, then I have to delete all the characters I'm taking from the first string. So if I is given, that's I deletions. And the symmetric case, if I don't take anything from the first string, I have to insert everything in the second string that I have. And in both cases, these are the number of operations. That's what we get as the cost. If we're not in these degenerate cases where I have no letters from one of the two strings, then I can always do the 3 options for the last step. This one says I'm taking one more character from the top string, but I leave the bottom one alone. So that's essentially like, shouldn't have drawn it like this, I guess. I'm deleting this character. In this case, I'm inserting one in the second string. That's why this is +1. This is for a deletion. This +1 is for an insertion. And the third case is I'm taking the last string of both characters, and then I get a cost of 1 if and only if they're different. So here again, this notation, I know it as Iverson bracket. That's how Don Knuth calls it. It's 1 if the condition is true and 0 otherwise. Let's say else. That's a concise way to write the recursion. These are the 3 options I have for the last column of the alignment, and I take the best. That's essentially all for the experts that know dynamic programming. The rest is completely mechanic. Let's go through it one time. At this level, we can already estimate what the final running time will be, because the number of subproblems is fixed now. That's all of those, n times m. That's an n. Sorry, which one was the n? Second. The time to optimize one specific subproblem is to find the minimum of these 3 items, so I can do that in constant time. So the overall time is n times m. N times m, hard to say clearly. In the trivial solution, that's also going to be my space requirement. And this is something we'll come back to. As I said, the first step is to just compute the costs, but we can do a backtrace to find the actual edit script. Just to illustrate the 4 steps very briefly, if you have this recursive equation, maybe you're concerned that it's costly to compute, but fear not. In the case where we have dynamic programming templates apply, we can always do this. We can always compute the recursion in a way that I don't have to recompute many things. If I memorize, I guess that's always possible. It's just the number of subproblems that's not too big. So the convenient way to do this is to have 2 mutually recursive functions, one that computes the actual value and another one that wraps it and says, oh, have I computed this subproblem? If yes, return the cached result. Otherwise, call the first function to compute the result. And for our concrete problem, this is what it looks like. The edit distance, that's the function that does the actual work, follows very closely the recurrence. You see the if statements exactly mirror the case distinction. Then I have to find this minimum of 3 things. So, okay, here I can just compute all 3 and take the minimum. It's really boring. And then the memoization part is to have a second function. That's the cached version of this computation. It starts, you have to, at some point, initialize this array of storing all the subproblem values. I'm doing this outside of this function and just assume this is already given. I somehow have a global variable storing this. And then in each step, I'm just going to check if my entry for this subproblem has already been computed. Then I return it. Otherwise, I first compute it. Again, the code is supposed to bore you to death because it's really showing we can stop at the level. As soon as we have this recurrence, we don't need to write down this code each time. It's very schematic and looks the same each time. This is often not the most efficient way to do it in practice because you're essentially doing unstructured random accesses to this two-dimensional array. And for cache locality, that's not perfect. You often do slightly better if you just fill up all the entries in this table bottom up. That's replacing recursive functions with for loops. And so that's another benefit in practice. It's not a huge factor. I don't know if maybe a factor 2 is already optimistic for this. Okay, but still, because it's always possible, it's kind of nice to spell it out. The general form means you're building a DAG over all the subproblems. The edges in the DAG come from which subproblem uses which other subproblem in one of the guesses. And it has to be a DAG, otherwise your recurrence wouldn't work. You would cyclically depend on each other. So it has a topological order, and you can fill the entries following this topological order. In most cases, the subproblems are tuples of numbers, and then if you pick the right order to iterate through them, you follow a topological order. But I think it's nice to keep in mind that this is it works in full generality. Here, much simpler. The subproblems were just the prefixes. I'm taking the first I characters from the first string A, the first J characters from the second string B. And the way they depend on each other, you can visualize, if you think about this matrix that we compute, Dij. Make it a bit nicer. So that's the matrix Dij that we're filling. Say I'm writing this in the way mathematicians would write a matrix, so 0, 0 is the top left corner. Then if I'm computing a certain entry, the three subproblems that this subproblem ij depends on are the three subproblems around it, namely the one with I minus 1, j minus 1, the one with I and j minus 1, and the one with that's one, and the one with I minus 1 and j. They correspond to the insert, delete, and replace / match. So the edges in the graph would look like this, and that's all edges. So you can do many things in this case to get a topological order, but one way to do it is to go row by row, and then within each row by increasing columns. Okay, that's a long way to say lexicographic by I and j. And here's the code for doing that. Lexicographic is very nice because that maps into two nested for loops. We first go over the rows, and then we go over the columns. And the inner part, again, is literally copying in what the recurrence tells us. There's the two base cases where we take the special starting conditions. And then there's the other case where I couldn't be bothered to write out finding the minimum again, so I just left it as a formula. But you would probably want to substitute the code from the previous slide. The magic here from the topological order is that whenever I'm using array values here, the topological order ensures that they've been computed before I reach this point, so I'm never accessing null pointers. That's what we have to make sure of. Where here, the initialization to infinity is irrelevant. Also, it's inconsistent with the comments. I think we don't use any of the values. We override every single one of them, so it doesn't even need to be initialized. Okay. I think so far is super easy. The last step is to compute the actual edit script. At this point, of course, you can analyze this algorithm, and it's 2 nested for loops. I'm sure you could do it. It's the same theta class as the memoized recursive function, but it tends to be faster, as I said, for essentially hardware reasons. But also the code, I guess, is a bit cleaner to write. The last step is, now we know from this table, like, okay, I didn't emphasize this, we return at the end the bottom right corner of the matrix that contains the edit distance of the full strings. That gives us the cost of the overall, or it gives us the edit distance, or the cost of the optimal edit script, but not a script or the alignment itself. If we wanted to get that, we can do, again, a very schematic and automatic translation to get a backtracing algorithm. Yeah, I couldn't fully track down where the name backtracing comes from, and it's not even always consistent. Sometimes people call this backtracking, and this is horribly wrong. Like, don't do that. There's no backtracking happening. So I'm strict on backtracing because we just retrace our steps, the steps we took to compute the optimal value. You can always write this as a queued recursive function. And here's the example for our edit script. I'm assuming I already have all the edit distance values computed, and I'm assuming I keep all of them around. So here we really need this m times n space. Then I have a recursive function that starts with the outermost sum. I would call it with m and n, the largest values for the entire subproblem. And the function is recursive. It has these conditions mirroring the recurrence. I regret I didn't have a small picture of the recurrence. We could have it, but maybe we can just puzzle it together again. If I is 0, I'm not taking any letters from the first string. So if I want to get to j letters from the second string, I have to insert them all. So I do that in my edit script. Similarly, if j is 0, then I have to get rid of all the I characters in the first string. So I'm doing that. The other cases that can happen is the last column in my alignment could be one of the 3 things. And here I have to distinguish if it's a match or a mismatch, because the operation in the edit script is different. First case is if my edit distance, if the minimum I'm computing for dij came from this option. So I'm going back in the j column, I'm getting rid of 1 character there. So that was an insertion. I kept the I characters from the first string, but I add 1 more in the second string. Well, if that was the best choice, that means the last operation in the edit script has to be the insertion of that last character in the second string. And how do I get the rest of the edit script? Well, recursively. So I've just called traceback on the subproblem that I'm picking the cost off here, and append this 1 more operation at the end. And the rest is completely symmetric. If the minimum came from choosing a deletion, then I'm doing that with the appropriate traceback. If the last characters, if I'm not in either of these cases, that means I could have had this one. I had a match in the last case, then I'm doing a traceback for all those, but I don't do any operation for the match because the edit script does nothing. Otherwise, the only option that's left is I did not do an insertion or deletion, but it wasn't a match, then it was a mismatch. I'm adding the replacement operation. Okay. If instead of producing the edit script, you wanted to produce the alignment, that's an easy exercise. The same kind of code. You just replace these edit script operations with appropriate pairs of characters. We could do that as an exercise, but I feel that's even too boring to do it. the time for doing the backtrace, if I have all the values stored, is dominated by computing the values, so I can always do it almost for free. And so computing the optimal cost and the actual solution have the same theta class complexity.